this morning, Hélène Esnault, who will talk about some fundamental groups in arithmetic geometry.
Okay, so thank you to the organizers for the kind invitation, and much more generally for the friendly and efficient organization of the whole conference. I can't speak for the first week, but can for the second one, and it was really wonderful, so thank you. And I would like to thank heartily Moritz Gertz and Lars Kindler and Takeshi Saito and Natsushi Shiro for their constructive comments and remarks on the slides. Also, I should say, giving a lecture after Peter's lecture is a challenging situation. So we take a rest. So the program today is I will the whole package of the Deligne conjectures as expressed partly in a very precise way and partly in a loose way in Vel 2. And we will start with the L-adic theory, and we will go on with the crystalline theory, as we see here. And that will be the first package before we move on to another analogy between characteristic 0 and characteristic P for local systems in the next days. So the one of the starting points, at least as I see the history here, starts with the theorem of Deligne in 87, where he showed a remarkable finiteness theorem, which is written on the board here. If X is a smooth connected variety over the field of complex numbers, and if we fix a rank R, then there are finitely many rank R Q local systems, which are direct factors of Q variation of polarizable pure hot structures of a given weight, and which are definable over Z. So definable over Z because there are general conjectures on whether variation of hot structures are definable over Z, and we don't know any answer. So this means that up to conjugation, the monodromy is defined over Z. And the prototype of this profound theorem by Deligne was the earlier work by Faltings. If we cut down the information here, we put weight 1. Then we deal with abelian schemes over base. And then this is a famous theorem of Faltings in the geometric situation, that there are finitely many isomorphist classes of abelian schemes on a variety without degenerations. In a given rank, of course, in a given genus. And the analogy Deligne proposed, and which he could prove in very recently, 3 years ago, is the following statement. If X, now defined over a finite field, is smooth quasi-projective, and we give ourselves a rank, but now, unlike in characteristic 0, we have to give ourselves some extra data, and the extra datum consists of we fix normal compactification of X, and we give ourselves a Cartier divisor, which is fixed and which is effective. And then the theorem tells us that there are finitely many irreducible Vel or étal rank R Lis QL bar shifts with ramification bounded by this Cartier divisor up to twist Vel twist or étal twist with the character of the base FQ. And remarkably, this number doesn't depend on the choice of L here.
May I ask the word will you explain?
So let me explain here. In fact, the definition owes a lot to the work of Moritz Gertz, who is here. And ramification bounded by a Cartier divisor means that whenever we map a curve to X non-trivially, then its compactification, the normal compactification at infinity, will map to X bar. So then we can pull back our sheaf, and we can pull back our Cartier divisor. It becomes a Cartier divisor on the compactified curve. And then to say that ramification is bounded by D, it means that for all such situations, the ramification of the QL bar additive on the curve will have swan bounded by D in some sense.
What is vague?
Pardon me?
What is vague?
Well, forget veil. Maybe it's not really the core of the lecture. Veil is that a veil representation which is étale is an étale, which is a continuous is an étale representation. So you allow a non-continuous representation of the Galois group of the ground field in the sense of veil de ligne. Is that okay? Okay. So thank you for the question. Pardon me? The number, because the line is telling us that there are finitely many irreducible representations, so it produces a number. The number.
Is there a formula for this number? Can you write down?
No, there is no formula. In fact, the line wrote a whole article to give one formula for P1 minus 3 points and P1 minus 4 points with prescribed specific monodromies at infinity, very specific ones, like 2 or 3 examples, and that's it. So we will, that's the answer. So I refer to the last chapter of our article with Maurice Kertz, who is here, and to the whole article of Deligne describing this number in those very, very specific cases. Okay? Okay, and the corollary here, which is very important, but in fact the proof of which predates the general finiteness theorem of the linear repeats that the model here is a model coming from Hodge theory, as we had in the previous lecture. Then this corollary is, of course, specific to our characteristic P situation. That means when we look at the eigenvalues of the Froebeni at all possible close points on a given QL bar sheaf here, then acting on the geometric fiber here at this close point, then all those eigenvalues are packed in a number field. I mean, a priori, it is a subset of QL bar, because the eigenvalues have to be in QL bar, but at the end of the day, this is a number field. So it's a very, very strong finiteness theorem. So now let me come to one, so to speak, main theme of our lectures. This is the Lefschetz theorem. The theorem, the complex theorem over the complex numbers of the line is in fact a theorem in dimension 1. Because when we are in characteristic 0, we know we have a good compactifications of our x here. And then it is a case that we have a Lefschetz theorem in the following shape. When we take a curve which is sufficiently ample and transversal to the divisor at infinity, then we have the Lefschetz theorem for the topological fundamental group. And consequently, to show finiteness for representation of the topological fundamental group of X reduces to a question on curve. We can assume that the dimension of the variety is 1. Now, in characteristic P, in higher dimension, we do not have a Lefschetz theorem at disposal, and in fact, it was already underlined in a quite strong way in Peter's lecture due to these huge families of Artin-Schreier coverings. This is the main obstruction. So the theorem of the line, this finiteness theorem of the line, is much more difficult and does not reduce to dimension 1. Yet one has the following Lefschetz theorem. I will list them in a certain order, which is the order I chose. It doesn't mean it's the only way to see the history. We have this remarkable theorem here of Drinfeld, which is also extremely recent. So as we know in characteristic P, we don't have good compactifications at disposal. So we take a projective normal compactification of X over a field. And then we remove at infinity a codimension 2 subset in such a way that the divisor at infinity becomes smooth.
So the word smoother just refers to X in the first line, not to X bar.
X is smooth from the scratch. First slide. We don't have resolution of singularities in characteristic P, so this was precisely what I explained just now. So we remove codimension 2 then in such a way that the divisor at infinity is smooth. And then the theorem of Drinfeld is telling us that it will be enough to look at the situation which is not proper, which is not projective, in order to obtain a full Lefschetz theorem for the term fundamental group. Namely, if we take C bar now, which is smooth projective, and hits the smooth boundary divisor in good position, then it will be the case that the term fundamental group of X is absorbed by the term fundamental group of the open curve. As a corollary, the finiteness theorem of Deligne, which we just saw before, the arithmetic finiteness of Deligne, which was here, if we put this ramification as a term ramification, as in characteristic 0, it reduces to a curve theorem, and then we will see later where it comes from.
Can I ask about the characteristic 0 case? You might have thought that the better analog would be for like D modules, possibly irregular.
We come to this either at the end of this lecture or next time.
Can I just, and in the characteristic 0 case, the statement was that if you have such a curve, then you get a surjection. But such curves always exist?
I don't understand the question. I mean, it's a complete intersection curve here, which hits the boundary in good position. Complete ample intersection curve. Okay. So this means that the Deligne theorem here, if the ramification is really bounded in the term situation, in the strongest possible way, then we obtain the Deligne theorem out of the corresponding theorem of a curve, on a curve which is by far not trivial. We will come to this in a minute. But it's a theorem on curves. And I want to underline here that in this theorem here, there is no need for good compactification. So we don't have to know resolution of singularities to obtain Drinfeld theorem. And the proof, and because it's nice and it's not hard, let me say in a word how Drinfeld does it. So he uses Bertini's theorem in order to preserve connectedness of a finite étal cover of X by restriction to C. And then he uses stemness here and transversality to keep smoothness of the pullback. And if a scheme is smooth and connected, then it is irreducible, and that proves surjectivity. So this is very nice. We will see an echo of this much later on in the crystalline situation, which refers to your question. So,
So conceivably, you need a little bit less than resolution to deal with all curves, right? You just need to resolve.
I don't understand the question. I don't know what all curves means. So I said that the theorem of Drinfeld is a theorem on the complete intersection curves, which are smooth. Okay. So now the theorem under the assumption of a good compactification has been enhanced by Lars Kindler, who is also here, to obtain a full package of a Lefschetz theorem here, where now, like for the topological fundamental group, not only the term fundamental group here is absorbed by the term fundamental group of a good curve, but it is really equal to the term fundamental group of a surface, of a good surface. But those theorems here, as I underlined, they are not enough to understand the deepness of the finiteness theorem of Deligne. One needs a different Lefschetz theorem in order to start with, and one can formulate them like this. And in fact, they go back to the work of Wiesent, and they were further adapted by Drinfeld in the same work I mentioned before. So let me mention them. On X quasi-projective smooth over finite field, we fix a number of closed points. So the vertical bars here means closed. So this is a finite set of closed points. So the two, I call them wide Lefschetz theorem here. they refer to two different situations. Either we give ourselves the L-adic sheaf, which is irreducible, and then we want to find a curve on which the L-adic sheaf remains irreducible. And then this is the first theorem. Once we give an irreducible QL bar, Vel, or étal sheaf, then there will be a curve which goes through the given closed points on which the irreducible representation stays irreducible. This is one theorem. And the second one is of a different flavor. We fix ourselves a finite quotient here. So that means we fix an open normal subgroup here. And then there will be a curve on which has the property that its fundamental group is subject onto the quotient here. So, and the proof here, I don't explain the details, but the proof uses Hilbert irreducibility à la Wiesent. And the corollary, now we come to the core of the matter here. The corollary, I'm sorry, where were we? Thank you. Thank you very much. So the corollary here yields the first part of the package of Delin's conjecture, namely QL bar adic sheaves have weights and they have companions. So let me say just in one word, I mean a little bit more than in one word. So the corollary is due to Drinfeld. Of course, I write corollary, but it's more than a corollary. So that's Delin's conjecture in Vel 2. If V is irreducible, has the torsion determinant, then V has weight 0. And if V is an irreducible Vel sheaf, again, QL bar Vel sheaf with determinant of finite order, so same assumption as here. I apologize, it's not very nicely written. And if we fix an automorphism of QL bar over Q, then there is another irreducible Vel Lie sheaves with QL bar coefficients. Let us call it V lower sigma, called the sigma companion with finite determinant, with determinant of finite order, such that all the local characteristic polynomials here of the local Frobeni are transported to each other via this automorphism of QL bar over Q. And the relation to what we explain on Lefschetz theorem here is that we reduce the problem to curves. The first reduction to curve was the first shape of the wide Lefschetz I gave. So we have to show here the existence of weights. And this is a corollary of Laforgue's main theorem on Langren's duality, that there are weights for irreducible QL bar sheaf with finite with torsion determinant on curves. And the second corollary here, the existence of companions, is coming from the second wide Lefschetz theorem, and it reduces, so to speak, but here it's much harder, the existence of companions to the existence of companions on curves, which is also the work of Laforgue. Go ahead. What?
Weight.
Ah, yeah, sure. I apologize. So weight here, this is coded here in this formulation here. When we have a close point, it has a Frobenius. So the Frobenius acts on the geometric stalks at this close point. So it becomes a QL bar vector space and a linear endomorphism, so it has eigenvalues, and those eigenvalues have weights. Once we fix a complex embedding, once we fix an identification of QL bar with C. But if we know a priori that those eigenvalues are in a much smaller field than QL bar, we don't have to fix an identification of QL bar with C. So those are the Lefschetz theorem which are used by Drinfeld and Delin. And inspired by the work of Delin here, Kertz and Shuji Saito recovered, so to speak, the abelian part of Delin's finiteness theorem, interpreting it as a good Lefschetz theorem again. And in fact, their Lefschetz theorem is even stronger because it doesn't say that some abelian fundamental group is absorbed by the abelian fundamental group of a curve, but it says that it is equal to the abelian fundamental group of a very good surface. So let me explain. If X is a smooth quasi-projective variety defined over a perfect field, and X bar, now we use the existence of good compactification, is an SNCD compactification, and D is an effective divisor supported at infinity. Then they define the abelian fundamental group with ramification D by the condition, by looking at the representation here, the characters, and then we request that those characters on curves, as said before, have bounded Artin conductor by this divisor D. And then under this definition of this abelian quotient here, then the Lefschetz theorem holds in the very strong form, namely for a very, very good ample intersection of ample divisors in good position with respect to infinity, then one has a full package of Lefschetz theorem. And of course, if X was dimension 1 with a very, very ampleness condition here, then it would be surjective. So this is very nice because well, very ample means it's not only ample. In fact, this very, very ampleness condition appears already in characteristic 0 when one tries to do a Lefschetz theorem for singular varieties. Just the ampleness is not enough, as demonstrated by Macpherson in his Morse theory, Koreski-Macpherson. It means that not only you need a section of ample divisor, but you need a section of a very, very ample divisor, and this very, very ample divisor depends on the type of it depends on the situation. I mean, you have to go to a high degree ample divisor. So I cannot give you a number here. I cannot give you.
It's not a specific definition of very, very ample.
Very ample means that not only for a given for an ample divisor, it's not going to do it, but for a high multiple of this one is going to do it. So, and then the corollary is a finiteness theorem as written here, that now if our ground field is no longer perfect in general, but it's really finite, then the kernel here of, of course, to say that, I should assume that K is really the field of constants of our variety here. Then the kernel of these abelian groups as defined by them to the abelian group of the ground field here is finite. And in particular, and this was the motivation, it implies the infiniteness theorem for sums of rank 1 Lifshitz. So, yeah, maybe I don't say anything on the proof here. So this raises very natural questions here for the higher rank case, so for the non-abelian part of the fundamental group, of the étal fundamental group as defined by Grothendieck. I'm not really talking at all on the generalization of SGS3 and given by Batt and Scholze. So that's really Grothendieck's fundamental group here. So one has a notion here of a least QL bar sheaf here, and which is just a representation here, with ramification bounded by D, and we discussed already, so this D is a Cartier divisor at infinity of a normal compactification. So we discussed already this notion here, but in a way which is reminiscent to Drinfeld's Lefschetz theorem for the TEM fundamental group, as explained at the beginning of the section on Lefschetz theorem for the TEM fundamental group. Lefschetz didn't need a good compactification for the TEM fundamental group. Then in the same spirit, Yu and Yang slightly changed the definition I gave you in such a way that it is able to define it without requesting a good compactification. So one would hope to use this idea here to generalize it and to generalize the work of Kers and Shuji Saito in order to be able to define a quotient here of the étale fundamental group with ramification bounded by D, which would generalize this group here, and which would echo, so to speak, which would reflect the Lin's finiteness theorem. That means one could ask, I don't know whether it's a reasonable question, but one could ask, if we had a reasonable definition of this quotient here, if we could absorb this quotient here by the corresponding quotient on the curve. And if we did, then it would give a pure, more conceptual proof, so to speak, of the Lin's finiteness theorem. One would understand it better. Okay, so
Can one absorb the fraction in the Q divisor by taking a branch couple right away?
I'm sorry, it was too fast.
Can you absorb the fractions in the Q divisor by just taking a branch couple right away, or is it somehow?
No, this is really bad. No, this is really bad. This is really, you know, as explained by Peter in his lecture, this uncontrolled part of the fundamental group. So see, Peter was talking on fields here, but it's already in SGA 1 that the étale fundamental group doesn't have any QNet formula. For example, if you take A2, then its fundamental group will be never absorbed by the fundamental group of any curve in A2. And that's the same as what Peter was saying. I mean, you can express it by QNet or you can express it by fields. That's the same phenomena. And so it gives a negative answer. Okay, so this here it was a sort of a resume and of the work of Drinfeld and Deligne on Deligne's conjecture, and then follow-ups, and then on what it is relying. And now the part which comes here, that's the Deligne's conjecture, which are expressed in a very, very, very loose way, and on which, unfortunately, there will be no complete answer at the end. So I will try. I thought a little bit of it why we don't have a complete answer. I'm not really a specialist here of crystalline theory, but what those theorems are concerned, in fact, it's easy to understand what is the main philosophy behind, and I'm trying to present here the way I see it, which is not to say that there are not other ways. Unfortunately, the first part is a little bit technical because I have to introduce a category of crystals we are dealing with. Otherwise, Dan is asking, will be asking even more questions. So I hope you read carefully what is on the slides, and all the definitions are given. So X is most geometrically connected over a perfect field, and W is a ring of it vectors. And we denote by capital K the field of fractions of the ring of it vectors of this perfect field. So now one defines the crystalline sites step by step. This is a very classical construction. As PDC cunning, so this is a category here, and the objects are here. There are PDC cunnings of Zariski opens here. So delta is a PD structure. I don't explain what are PD structures. And the coverings are coming from the Zariski opens here. So this defines the site.
What does PD stand for?
Divided powers in French. Okay, and then we consider X over W as the limit of those sites here. And then we will define a category of crystals. So now there are many, many categories of crystals, and you will see in the second lecture, most particularly conjecture by Johan, talking on isocrystals and discussing with him during the second week, last week, on this, he himself was no longer very sure what category of isocrystals. So there are many categories of crystals to be considered, but for Delin's conjecture in Vel2, I would think there is mostly one category, and I will try to come to it step by step. So, oops, do we have a pointer? Yeah. So the category of crystals, first one has to understand what means a crystal here. So once we have a site here, we can define sheaves of abelian groups, and we can also define sheaves of modules over the structure ring here, the ring of functions here on each thickening. And then, so those are sheaves. So we have transition maps, and crystal means that the transition maps are isomorphism. So this is the definition for crystal. So they are sheaves of OX over W modules of finite presentation, also called coherent O modules, which transition maps which are isomorphism. So we denote this category by Chris here, X over W, and this is a W linear category, which means that the harms in this category are W modules of finite type. Transition maps for definition of sheaves are isomorphism. So now we define the category of isocrystals as a Q-linearization of the category of crystals. So Q-linearization of a category means that the objects are the same, and the homomorphism, which in the category we Q-linearize where W linear, becomes capital K linear, which was a field of fractions. That means we tensor by Q. So the objects are the same, but the isomorphisms are not, the morphisms are not, and then this enables one to have several possible writing of the same object here via those new isomorphisms which we didn't have before. And then the absolute Frobenius is acting on this category here of isocrystals. And this one way to define it is that this is the largest false subcategory on which every object is F infinity divisible. I'm sorry, the Frobenius is acting, and one way to, I apologize, one way to define the category of convergent isocrystal, as defined by Berthelot-August in a slightly different manner, is to say that this is a false subcategory here, the object of which are those which are infinitely many times Frobenius divisible. August defines directly this subcategory here by defining a site which is not the crystalline site. This is the site of enlargements, and considering the convergent isocrystals, which are crystals now no longer of OX over W modules, but OX over capital K modules over, let's say, affines here, a finite presentation. But at the end, this is equivalent to this category, which we can define purely algebraically without new sites in this manner here. So this is one category. Those two categories, here the category of isocrystals and the category of convergent isocrystal, both will play a role later on. So we keep them in mind. And then there is a category which will be closer to the Lin's ideas, which is a category of F convergent isocrystals. And this one is defined by, so that means it's really a subcategory of the category of convergent isocrystals, on which, I mean, every object here was Frobenius divisible, but now the further requirement is that we fix a root, a Frobenius root of this isocrystal, and this Frobenius root is precisely E itself. So this is a definition, and because of the appearance here of this extra datum in the definition here, this category now is QP linear and Tanakian. I mean, it was, this one, I don't know whether I said, this one was capital K Tanakian, this one is QP Tanakian. And then once we have this convergent category here, so there is a complicated definition of F over convergent isocrystals. I will not give the definition. In fact, I'm not the most competent person to do it. But at any rate, yet again, we will use, so to speak, a purely algebraic aspect of it, as we did earlier on. Maybe I go back here. For the category of convergent isocrystal, the definition we gave was purely in terms of the action of Frobenius. And here, we do the same thing thanks to the work of Kedlaya. He defined on this complicated definition here, which is initially due to Berthelot, functor, which is fully faithful. So we can think of it as being a first subcategory of this category, which is much easier to understand. And then I don't give the definition, but I give a loose terminology here, which in fact is coming from Kedlaya, is that it's a category where something like unipotent local monodromy holds after alteration. So I come to this in a moment because the guiding line of the program of Deligne, as we know, is complex theory, the theory of variation of odd structures over the field of complex numbers. And precisely this formulation here is basically enforced by this analogy. We will see immediately how. So Briscoe, over the field of complex numbers, showed by transcendental methods, in fact by pure transcendental methods, which were overtaken much later on by Simpson in order to prove analog theorem on existence of torsion points, I mean, in a sort of Manin-Mumford type question for local system. I don't go into this. So Briscoe proved by transcendental methods that the Gauss-Manin connections in complex geometry have quasi-unipotent local monodromies. So his proof is not very difficult, but it's a very essential theorem because it is a guiding line for finding the analogs over a finite field. So one way to formulate that one has quasi-unipotent local monodromies is by saying that it becomes unipotent, and here one should say in general after an alteration, like Johann de Jong. But in fact, using in characteristic 0 Kawamata's trick, in this situation here, we can say that it becomes unipotent after a finite cover, which is possibly ramified outside of the boundary divisor. So Grothendieck over FQ proved the analog theorem, namely that least QL bar shifts have quasi-unipotent local monodromy. And here local monodromy, this refers to the action of the local inertia, the L of 1, L being not P. Now, Kedlaya here generalized those, I mean, not generalized, but found the correct analog of those two theorems here for the category of F over convergent isocrystals here. And his theorem, so there is a local theorem and a global theorem. And here it is formulated in a global way, but it uses the local result, which is due to himself and Yvan Dream-McBook, that those F over convergent isocrystals have unipotent monodromy at infinity after an alteration of the variety over a finite field. Well, I apologize. Over the field K, finite here doesn't play any role yet. It will come later on. So in particular, I want to underline that, I want to underline here that there are blow-ups at infinity. And this is analog to the resolution of turning points over C for irregular connections. Again, a theorem which is due to Kedlaya and independently to Mochizuki. And in a very interesting manner, Mochizuki is using a characteristic P method in order to prove his theorem. and in particular the behavior of the P curvature. So I believe that even though it is not worked out, there is an intimate relation between the two proofs here. But for us here, and for later, if X is proper, just by the loose definition I gave, this category of F over convergent isocrystals here is just the same as the category of F convergent isocrystal, and this one had a very simple definition in terms of F divisibility. I mean, the convergent category has a very simple definition, and F convergent category has a very simple definition. So the problem here, the difficulty of this category here, comes from the ramification at infinity. And I can go on here. So over FQ, there is a slight abuse of notation in the literature. One defines the category of F over convergent isocrystals, which is considered as, in fact, if one refers to the previous definition, is a category of Fs convergent isocrystal, where S is a power of P here. So it becomes linear over capital K being the field of fractions of the Witt vectors over FQ. So there is an abuse of notation here. And then one can L linearize for any L which is algebraic over capital K. And at the end, it defines this category over QP bar here. So we are talking briefly on this category now. So the analogy which is expected, so now I come back to Deligne. As I said, Deligne formulates a phrase which is just, in fact, not even a phrase. It basically doesn't have a verb. It's a very small remark. So, but here we try to formulate slightly more precisely the analogy. So the analogy between C and FQ, L-adic, and the expected analogy over FQ p-adic. So the irreducible objects here in this category of F over convergent isocrystals over QP bar. I recall we are over FQ here. I want to insist it's not for any field, any perfect field, with finite determinant. This should be analogs. I wrote R here, but in fact it's a typo. I say this should be analog in some sense to irreducible QL bar shifts. And here I'm loose here. I didn't write etal or vel, let's say etal. QL bar shifts with finite, but anyways, finite determinant, so no problem. So I apologize for the comment here. And open bounding ramification at infinity, and here it starts immediately. What is the correct notion of bounding ramification at infinity for F over convergent isocrystals as we define here? What is that? But let's say there is a good notion here, then it should be analog. So if we could perform here this analogy, then it should be done in such a way that they are analog over C to irreducible Q variation of polarizable hot structures. I should say irreducible. I forgot to write irreducible here. No, it's here. I apologize. Of pure weight definable over Z. So those should be, so to speak, the analogies. And as we saw already, we had an analogy between this and this. The question is whether we can pack in the Line stream here this line here by being able, notably, but not only, of course, this would be one step among many other ones, one can define a good ramification theory. So what we have now, we come back to the only precise formulation Deligne gave in his Vel2. He calls on petits camarades cristallins. And this has been proven on a curve by Abe. That's a crystalline version of Laforgue's theorem, which was not Deligne's formulation. Deligne was in general for a normal variety over finite field. In fact, I should have said that at the very beginning. Drinfeld and Deligne do not prove in general the conjecture. They have to go from a normal variety to smooth variety in order to solve in order to be able to solve it. So it's still open in the L-adic version of a normal variety. I should have underlined that. But here we have a smooth curve here, and then Abe proves that an irreducible over-convergent QPF isocrystal, so with the definition we had earlier on here, maybe I should, this is this definition here when we have a finite field and we start at some level and then we linearize here to QP bar. So he showed that there is a notion of weight here, which is due to Kedlaya. And it is completely analog to the notion of weights we had on L-adic shifts. It goes via the local Frobeni at close point, and then on the geometric point over this close point, and then looking at the eigenvalues and looking at the P valuation. So it's iota pure. So iota refers to the complex embedding of our field here. So then those which are irreducible over convergent with finite determinant do have weight 0. So it's already remarkable. And then it enables him to construct a direct analogy between those QP bar F isocrystals companion, the definition of which we gave for L-adic shifts. I don't recall it. And this way, we have a pure, in fact, a pure correspondence between, it's more than an analogy, it's a correspondence between QP bar F isocrystals and QL bar relative shifts, always under the assumption that it's irreducible and it has finite determinant. So it's quite remarkable, yet it doesn't really, for people, for geometers, for example, for me, but for many people, it doesn't solve at all the general question. And the reason is we have no wide Lefschetz. This terminology here was the one we had at the beginning of our slides. We defined the term Lefschetz theorem, which was due to Drinfeld. And then we had two wide Lefschetz theorem. One, when we fix a representation which is irreducible, we want to find a curve on which it stays irreducible. The second one, we fix a finite quotient of the étale fundamental group. And then we want to find a curve which the fundamental group of which recognizes completely this finite quotient. We don't have that in the world of F over convergent isocrystals. So in particular, the conclusion we can draw from this poor information here, that we don't have those wide Lefschetz theorem, is that one does not know whether irreducible F isocrystals with finite determinant are iota pure of weight 0 on X smooth quasi-projective over finite field, because you remember from the L-adic theory, one used this fact here, starting from Laforgue's theorem, and we had one object, and then it was irreducible, and then we could apply the first wide theorem I was telling you, the one which finds the curve according to the representation. The curve is attached to the representation. So one does not know whether those F isocrystals here, when we have a finite field, are iota pure. A fortiori, one does not have a number field capturing the eigenvalues of the local Frobeni here, acting on close points. Nor does one have a crystalline version of the finiteness theorem. So there is no higher dimensional generalization of the package which consists of Drinfeld's theorem and Deline's theorem in the L-adic world. What we have, it's not a Lefschetz theorem, and this is the end of the lecture for today. It is something which is much weaker, but we will see later on, we will see next time, on Wednesday, in the next lecture, that even though this theorem, which I haven't yet read, seems to be weaker. It enables one to show a tiny bit of something. So that's the theorem of Abbe again. So if X is quasi-projective smooth over finite field, iota pure or mix, in fact, I didn't say anything about mix. It doesn't really matter here for the discussion. Semi-simple objects in the category we described, F over convergent isocrystals, are determined by their local eigenvalues at close points. This means, said properly, I mean, I was loose in the formulation here. It says that if we fix two such objects here, and if their local Frobeni here have the same eigenvalues at close points, then in fact the semi-simplification, or if we start with semi-simple objects, the two objects are isomorphic. So we will use it in the sequel. So it's of course not a Lefschetz theorem, but it's not too far from a Lefschetz theorem, and it enables to say a tiny bit of something on some weaker aspect of those questions here. So thank you very much.
So the proof I know of this theorem in like the École case goes by reduction to curves. Is this the same? I mean, does this also get proven by reduction to curves, or is it?
No, because I think, okay, I cannot answer with high precision, but I can say like this, the answer should be no, because we don't have a theorem, a Lefschetz theorem, which enables us to reduce to curve. So it is, but in a way it's not completely no, because it goes via the zeta function, looking at the poles of the L functions. And so in a way, it's not too far. But it's not really reducing to curves the way I think you think. I'm not quite sure, but yeah.